This video, along with all course content, including laboratory and hands-on activities, were developed by Andrew S. Heinz, PhD, and are copyrighted 2016, 2018, and 2020. All rights reserved. The student's course handbook serves as a guide and as a resource to the student throughout the course. It contains the sample problems done during class, laboratory activities, and practice problems to develop knowledge outside of the classroom. It is available on Amazon. All right, we do have quite a bit to get through tonight, so I want to make sure we're starting right on time. So how are we all doing? Good? Everyone's nice and healthy? At least the ones here? Good. All right, so you guys can remind me, because I'm very forgetful, what did we talk about last week? Jeremy, what did we talk about last week?
Civil engineering.
Civil engineering and mechanical? Cool. What specifically were we talking about in the lecture?
Mechanical structures.
Mechanical structures, specifically. What do we build at the end of class?
Beams.
Beams and bridges, right? Yeah. So what we were talking about last week was statics, right? So if I don't want my building to fall down, what does it have to be in, Vikram?
Stationary location.
In stationary location, right? It has to be under equilibrium, right? It has to be able to, because remember, what's my formula for force? F equals ma, and what's m? Mass, and what's a? Acceleration. So in order for my building to not be going anywhere, it has to not be accelerating, which means that the net force on it has to be what? Yeah, to be 0 on one side of the equation, have to be 0 on the other side of the equation, right? So net forces, all the adding up forces have to be 0, meaning if it's wind's blowing back, has to get a pushback from the ground or something like that, or the materials in the building. All right, so yeah, that's pretty much what we talked about last week. All right, whole cool subject to go through, but we only had an hour, so I had to pick part of it. All right, so tonight we're going to be talking about electrical circuits. You guys have probably already done some talk with electricity and circuits in your physics class, I'm sure, at this point. So obviously we're going to run through the basics first, but then we're going to go more into kind of the applied engineering design part of it at the end, right, with resistivity and kind of how we would connect lights and stuff like that. All right, so first, electrical circuits is a class that every single engineer is likely going to take. I can't think of any off the top of my head that do not take it. And usually it's like I think I took it first semester. I'm pretty sure I took it first semester. All right. So obviously, the primary people who would be concerned with this, though, are electrical and electronic engineers. So does anybody know what the difference between an electrical engineer and an electronics engineer is? What do you think, Kate?
This might be wrong, but I think of electronics, I think of more complicated, like electricity in more of a device.
Mm-hmm. Electricity in a device.
Yeah, whereas electrical just maybe be like power lines.
That is an excellent spot-on answer. Yes, and that's what it really boils down to, right? So electrical engineers work on supplying the electricity for the most part, right? Generating it, supplying it, and getting it where it needs to go. And the electronics engineers, as you aptly put, work on the devices really that consume power, right? So one side works on generating and transmitting it, and the other side works on really using it, right? Now, of course, as with everything in the engineering world, that's very fluid. Things can change, right? Just because you're trained as one doesn't mean you can't work in the other field, right? You can move around. But so EEs, as we call them, electrical engineers, design, develop, and oversee the manufacturing and implementation of electrical equipment and devices. So in the past, he was not available to come this year, but in the past we've had an electrical engineer friend of mine from Eaton, which is a big company down in Wilsonville, and they make power generating equipment even out at Bonneville. They handle all the stuff out at Intel for us as well. Okay. And again, because much of the training of these two is the same, especially in school, it's really just kind of, even though you may be an electronics engineer or an electrical engineer, you're really going to get the same degree in school, and the rest is going to be just kind of your learning and your career going forward and what you do. Okay? So electrical engineer, like we said, design and test the manufacture of electrical equipment, involved in the design and maintenance of power generation, right? So they may deal with motors or generators or something like that, whereas our electronic engineers are going to use that electricity to do devices, right? So an electronics engineer may be involved in designing your phone, right? We have electronics engineer that help design our chips, of course, right, before we rebuild them in my factory, and so on and so on. Do note that, of course, these days, as you would expect, electronics engineers work closely in a lot of fields related with computers. And remember, the definition of what a computer is has certainly changed. It's not that big box that sits on your desktop anymore, right? Your phone is a computer, a calculator is a computer, right? My watch is a computer, right? So you'll be working stuff with that. So you will also be working very closely with hardware engineers, because obviously you have to make sure that the components you're designing actually work with what you want it to do. Okay? All right, so electrical engineer, 2016 median pay. I didn't have a picture, so I threw in my little guy here. Right, but 2016 median pay is $96,000 a year for electrical engineers. Very highly paid field. However, it's not really however. That's in comparison to the other fields. That's because it's easier in this field to continue to progress up the chain and still be called an electrical engineer, whereas as a civil engineer, you may no longer be considered an engineer. You may be a manager at that point, if that makes sense, right? So whereas civil engineers were paid, I think if off the top of my head, like almost 10 grand less, that's because at that point you may not actually be considered to be a civil engineer anymore. You may be in administration or policy or something like that, right? And then you'll see that a lot with environmental engineers. Environmental engineers are historically underpaid compared to the rest of the, and they're not, but the actual environmental engineer side is historically underpaid, because at that point they become a regulator or something like that, right? They're still fundamentally an engineer at heart, it's just their job title is not that, as far as, again, the Bureau of Labor Statistics. So electrical engineers, of course, and they're getting paid a lot of money. And again, remember, like I said, we don't ever calculate that per hour because it makes you sad. As for job outlook, they are growing a little slower than civil engineering that we looked at last week, which is 7%, but that's about on par with the rest of the economy. So that's perfectly fine. All right, top schools for electrical engineering. We see MIT, we see that on there again. We have Stanford, we have UC Berkeley, go hang out with all the hippies, Georgia Tech, and then University of Michigan. So those are the top 5 schools as of 2018 for, it says undergraduate civil at the bottom, but that is for electrical engineering. All right, so let's talk about circuits. So first off, Aditi, what is a circuit?
It's kind of a successive chain of like electricity in motion, like flow of motion.
Perfect. It facilitates the flow of electricity, right? So let's start off with, what is electricity? What do you think?
Electricity, like a power or energy.
Power, energy. Okay, what is electricity?
Moving electrons.
Moving electrons, right? That's correct, right? So electricity is the flow of electrical charges, which are electrons, right, around a circuit. So in circuits, the most common carrier is, of course, the electron, like we just said. And basically, right now, let's see, this is my wire, right? And I've got a bunch of circles in here to represent the atoms that make up the metal in that wire, okay? These little red dots, those are our free electrons that kind of exist in the bonding cloud. Before we move on, can anybody describe metallic bonding to me real quick from a chemical standpoint, chemistry standpoint? What do you think?
The attraction, formed by the attraction of to a sea of delocalized electrons.
A sea of electrons. You just said it perfectly, right? So I want you to think of, I already picked on UC Berkeley, right? So I want you to think of metallic bonding as basically a hippie commune, right? So if we look at the metals in the middle of our periodic table here, generally in this area, these guys don't have full shells, and they're kind of in that +3, +4 range to where they could kind of go either way, right? So what they do when they're with other metals is they say, all right, I'm a copper and you're a copper, and together we don't have, right, it's just like hippies, together we don't have enough money, right? Together we don't have enough electrons. What we're going to do is we're all going to go live out on this farm, and we're all going to contribute together. So at any one time, one of those atoms, one of those hippies can have everything they need, but somebody else doesn't. Right? So what they do is they donate their outer shell electrons to the cloud, which forms a sea of electrons. What would be the charge then of that cloud? What's the charge on an electron? Negative, right? So we have this big negative cloud, and we have all these now positive shells in the middle, right? So we get this overall neutral thing, but what this actually does is it makes them stick together. The cloud itself is basically acting as like a fluid glue magnet sort of thing to kind of keep everybody happy. So at any given time, any one individual is happy because he has enough, but collectively they don't, and that's why it maintains neutrality. So the reason that that's important from an electrical point of view, right, is we look at something like copper, right, which I used as the example. Copper, we know, is used in wires, and that's because when it kicks those electrons off into the cloud, those electrons are thus more mobile than they would be if they were stuck in like a copper oxide or something like that, which is actually an insulator, right? So those electrons are very easy to move, so it doesn't take as much of a push for us to get those electrons to move down the line. So if we apply a charge, like let's say to our copper here, if we apply a charge to one side, we can actually, so these electrons normally they're bouncing around like this, and as we apply a charge, we can actually get those electrons to behave and travel in the order that we want them to, going down the line, right? So as those electrons pass through, they can power our motors, they can do a lot of things for us, right? It's just electricity, right? That's what's going through our lights right now. Any questions on that? I know that's a pretty technical deep dive as to why it actually works, right? But again, we've talked about this, that engineering's not just one thing. You have to understand chemistry, you have to understand physics, you have to understand math, you have to understand the whole picture to really understand it, right? And that's fundamentally why a metal is really conductive, is because those electrons are really loose and can easily be pushed in the direction that we want them to go. All right, any questions on that? All right, great. All right, so charge, the Coulomb, has anybody heard of Coulomb before? The Coulomb is all right, perfect, is the fundamental unit of electrical charge. It is, and you have to memorize this, of course, because that's how we roll here, right? 6.24 times 10 to the 8th electrons is 1 Coulomb, which means, of course, is the inverse of that. So it's basically really, really small. How did they come up with that? Who cares, right? That's just the way it is, all right? So 6.24 times 10 to the 18th, that's a lot. That is not, note Avogadro's number. That is not a mole, because Avogadro's number is what? 6.02 times 10 to the 23rd, right? All right, very good. All right, so that leaves us with electric current. The continuous movement of charge through a circuit is called an electric current. That's what we call it, okay? And it's very simple. All we do is really, we just think about it as if we put a little tick mark somewhere along the line. We count how many of those charges pass that given area per time. Very simple. Now we give this units called amperes, right? So our current is a charge per time, and current is noted by capital letter I, which we'll see that in a second, but it has units of amperes. An ampere is actually a coulomb per second, right? That's the unit of an ampere. But we actually use amperes as a base, amps. We use amps as a base unit, right? You guys have all heard of amps probably when you were like 7 years old at some point, right? All right, so that's very simply it. An ampere, an amp, is a coulomb per second. And that's really fundamentally the last time that you're going to have to worry about coulombs, right? So sometimes you can actually you'll get some problems that are fundamental to the science, which is I have so much charge going through, calculate what my current is. Those will be very basic questions, and then you'll move on it beyond like 1.5 weeks of class, and you'll never see it again, okay? So electric current, like we said, is the flow of electrons around a current. So remind me, the charge on an electron is what? Negative. And negative things like to go towards what? Positive, right? Because then everybody's happy, right? Everybody's neutral and everybody's happy. So if we have a battery hooked up to a light bulb, the electrons are going to flow from the negative side to the positive side. Negative side to the positive side, right? Because in a battery such as this, it's an electrochemical cell. And the whole idea here is that we have something that's negative on one side, something that's positive on the other side, and the electrons rush around because they want to get to the other side and satisfy neutrality, right? And that's why your battery will eventually die, is because eventually it'll all be full, everything will be electrically neutral, and your battery's dead. All right? So everyone gets it. Electrons flow from what to what? Negative to positive. All right. Important not only just because it's right, but it's also very important once we get to semiconductors later in the year. All right, so voltage. In order for a charge to flow, it needs a push. That push is a voltage, right? We've all heard of volts, I would assume, right? If you've heard of amps, you've definitely heard of volts, right? That force is pushing, it's called voltage. Voltage is really just a measure of potential energy. Actually, it's not really just, it is a measure of potential energy, right? It's no different than your physics things where you say, I have a book this high, what's the potential energy of the book? How much does it release as it drops to the floor, right? It's essentially the same thing. If I have X amount of potential energy in volts, and I expend it, I can do that much work effectively with that energy. Okay? And in circuits, voltage is noted by the capital letter V and has units of volts. That one's super easy. Remind me, what's the symbol for amps? I. That's correct. I don't know why. All right, next, the third and last component we need for now is resistance. What is resistance? What do you think?
Maybe difficult it is for electrons to move.
Yeah, exactly. So what's a resistance band like in the gym, right? What does that do?
I guess that you have to pull really hard to stretch it.
Yeah, it pulls back as you, right? It's how you get all jacked in the gym, right? You go in there and you work out, right? Right. So the resistance is the inherentness of the system to push back, right? So something like a copper, like we were talking about with those free electrons, it's going to have very low resistance, or it's going to have lower resistance because those electrons are free. Something else like we talked about, like a ceramic or something where everything's tied together, or like a wood or a polymer or something like that, is going to be those electrons are going to be much tighter, and you're going to have a much higher resistance. Okay? So let's think about this fundamentally before we go into the equation. If we push hard on something and there's a lot of resistance, do we expect it to move far or move less? Move less, right? If I push on, all right, think about it this way. If I use the same force to push a 300-pound man, is he going to go farther or less than if I push on a 100-pound man? Obviously, he's going to go less, right? And that's fundamentally the same thing here. If we take our 4.5 volt battery and we hook it up to wood, we're not going to get much electrical current through that wood, right? But if I hook it up to a wire, we're going to go crazy and power our lights, okay? So it's the same concept. And then resistance is noted by the symbol R and has units ohms, which is denoted by the Greek letter. Which one's that one? Omega, right? Alpha and omega. All right, so that takes us to Ohm's law, the number one fundamental thing of all circuits, right? In a conductor, the current between 2 points is directly proportional to the voltage between those 2 points. In other words, I equals V over R, or the one that I think most people prefer is V equals IR. They're exactly the same. You can also do R equals V over I, because why? Because of math, right? So Ohm's law, so somebody remind me, what is this one? Volts equals amps or current times resistance, right? So fundamentally what that's showing us is exactly what I was trying to do with the big guy and the little guy in the same force, right? If I apply the same volts to a higher R, what has to happen to my I? In order to, right, so if I have, let's think about it this way. IR equals IR, same voltage, so let's put the two equations together. I1 R1 equals I2 R2. If R2 is larger, what does I2 have to be? It has to be smaller, otherwise they wouldn't balance out, right? It's just proportions, okay? Very good, guys. All right, so if you could please open your course handbook to page 16. We have a very, very simple question. If I hook a 9-volt battery up to a copper wire that has an inherent resistance of 2 ohms, what is the current through that wire? Who wants to tell me right now, because you don't need a calculator? 4.5, are you sure? All right, I agree, yes. It's 9 divided by 2, which equals 4.5 amps. All right, slam dunk, super easy. You just passed the first day of circuits, you can go home. All right, great. All right, so that takes us to the simple electrical circuit. So in order for us to actually build a circuit to make electrons flow, to turn on these lights, we have to have 3 fundamental things. What's the first thing we need? A light, okay. A load is what we'll call that, but very good. What's the second thing we need? A power source, good. And then what's the third thing we need? A wire. And can that wire just be laying out there? Yeah, it has to connect it all, right? So you nailed it, right? It has to be a closed circuit. So that's what we need, is we need a continuous conductive path that allows for movement of free electrons, right? And the reason it has to be connected from source to drain, right, all the way around the battery, is because what happens if I push on you and you have nowhere to go? It's just going to clog up and it's not going to go anywhere, which means we have no flow, right? In has to equal out, otherwise the world stops working, right? All right. So then we have a source, such as a battery or an outlet, and then we have a load, a light bulb, okay? So some elements in a circuit supply energy, and these are called, I already used the term, but this is a source. What would be the source? It would be your battery. And then we have the load, which is our light bulb, our fan, our camera, whatever it may be. Right, so this is a very, very, very simple circuit. We have a battery, and we have a light that is connected. Those are completely closed, and that brings us to what's called a circuit diagram. Okay, so a circuit diagram, instead of doing all the work of drawing the battery and the light and the wires, which takes forever, we can simplify it and we can do this ugly looking box thing, but they're super efficient once you start getting big. Right, so we have our battery, which is represented here. We have our resistor, which is represented here by the squiggly line. And then we draw the direction that the current goes around and label that I. That is our circuit diagram. Okay, pretty simple, right? So if you could please go to page 14 in your book. I'll give you guys a minute. If you could please draw a circuit diagram for what you see there. All right, everybody got it? All right, so I'm just going to show what I have, and you can see if it matches with yours. So the solution that I have is this. So I drew two resistors for R1 and R2. Now, if those light bulbs were equivalent, what could we actually, they don't have to be equivalent. If we wanted to, we could just draw it with one total resistor, RT, right, where we actually add up the resistances. I tend to, especially from a learning perspective, like to do each individual one because they may be different. You may have to be solving for an unknown, right? So generally, I find it's a better practice to draw each resistor in. However, as you'll see later, it is perfectly fine to just sum the resistances and put them all together. Okay, so I would also have accepted here the battery, the wire with just one squiggle. All right, page 14, number 2. Go ahead and give you a quick 30 seconds. Draw this one. All right, I see heads popping up. So here's what I drew. I drew our parallel circuit where I have our source and then I have the two squiggles here. It is also okay to have drawn it. Right, I drew them both essentially on one branch together. It is also acceptable to have drawn it like this. That is also an acceptable way to draw it. All right. All right, so now here's the last one on that same page. Go ahead and take 30 seconds and draw this circuit diagram, please. All right, why is this one a little more complicated? It's not? Okay, fair enough. All right, so here's what I drew. I drew basically the same thing as last time, except that one of those lines also has a resistor on it. Okay, so we have R1, R2, R3, however we define it, and then we have it all drawn out. Okay, and again, you could have done something very similar here, where just one of those lines has a resistor on it. However, could I have put the resistor here? Well, this is my battery. Could I have put the resistor here? Why? Right, so it has to be here, right? Or here. It has to be outside of the two. Very good. All right, next it brings us to switches. So when I go turn on a light switch, what am I doing? I'm closing the switch. All right, we got a couple people who already know the trick. I love it. All right, yeah, so a switch is this little device here. And it has two states, which are open or closed. So from now on, you are no longer turning on a switch or turning off a switch. That actually doesn't make any sense. What you're doing is you are turning on the device that the switch controls. Okay? It does matter, again, once we get to transistors later on in the semester. Okay? So if a switch is closed, the circuit now provides for continuous path. Because remember, we have to be able to get those electrons from one side of the battery to the other. If the path is open, or if we break that wire, they can't flow, and nothing will go through the light, and the light will be off. Okay? So by closing that circuit, we make a circuit. By closing the switch, sorry, we make a circuit, and it can flow, and the light turns on. On the flip side, if we open the switch, what happens to my light? What's that? Yeah, we open the circuit, right? And the light will turn off, and current will be unable to flow. Okay, so does anybody know why this associates itself to ones and zeros? Why? Right, and you guys will see that. Let's see if we have any. You guys have seen that on power, like power toggle switches before. It'll have a line on one side and a circle on the other, right? The line stands for what? well, 1, yes, but it also stands for closed. And the O, not the O, the circle stands for open, okay, which means that on, off, okay? So yes, again, so if we open our switch, a little animation here, light turns off, and we close our switch, and boom, our light's back on, our little yellow light. All right, so that brings us to a series circuit. So series circuit is the simplest, well, the simple circuit is the one with just 1 in there, right? But a series circuit is very fundamental, okay? In a series circuit, the same electron has to travel through every single load on that circuit before it returns to the battery, okay? Why does that matter, do you think, Andrew?
Well, matter is, I mean, it's going to have a higher resistance.
Mm-hmm. That's very good.
So if you consider all of something in a series, the total resistance, then the current must decrease as you add stuff to the series.
That's correct. So it's harder to push. And we'll get there in a second, but it's harder to push through a series versus a parallel, right? But so in a series circuit, each device is connected in a manner such there's only one pathway by which charge can flow, right? So now let me ask the question: what happens if one of those light bulbs breaks? What's that? They'll stop glowing. Why do they stop glowing? We basically just opened a switch, right? The light bulb broke, the electrons can't move, the whole circuit turns off. All right, so in a series circuit, because there's only one path for current to flow, that means that through each load, the current has to be the same, right? By definition. We're getting so many electrons per second through one, and I have to get the same through the second one, otherwise what happens? I get a pile up somewhere and everything stops moving, right? So by definition, every single load on that circuit has to have the same current, which is super awesome for us to go in and solve the problem. Okay? However, as Andrew was alluding, the total resistance of the circuit is a sum of the resistance of all those lights. Right? So in this case here, we had 3 lights on our circuit. So if we assume all of those lights are the same, we would have a resistance of what? 3R, whatever it is, right? 3R. Okay, so in this case, it's series is R1 plus R2 plus Rn. N being infinite, right? All of the components, no matter how many, must carry the same current. And that's fundamental for a series circuit. Are these lights here on series? No? What are they on? Parallel, right. All right, so let's go ahead. Well, let's do this first. All right. So that brings us to, so let's remember our Ohm's law, right? What's Ohm's law again? V equals what? V equals IR, okay? So series circuit voltage, because the current's the same through each component, the total voltage across the circuit is thus equal to the sum of the voltage consumed by each individual component, right? And that makes sense, right? As it goes through the first light, it consumes power, right? It consumes energy by powering that light, right? V equals IR. And then the next one is V equals IR. The next one is V equals IR. But remember, the current is the same across each one of those lights. So what that leads us to using Ohm's law is that the voltage of the series circuit equals the voltage consumed by each one of those lights. Or individually, that means you can actually go back and start doing your algebra, start doing your math, and if you have an unknown, you can easily solve for the unknown voltage or the unknown power voltage consumption, a voltage drop across that individual component. Okay? And that brings us to this term. The amount of voltage lost over a single component is called the voltage drop. Okay, that's a term that you will hear ubiquitously in circuits. Okay. So if you go to page 17, please, we're going to do what's called solving a circuit. So when we talk about solving a circuit, what we're going to do is go figure out each unknown on that circuit. So in this case, what is our unknown? I, right? And it's IT because that's the total current in the circuit, right? If I wanted to know what the current going through the 3 ohm resistor would be, what would it be? It'd be like I3. Current through I5 would be what? I5, or current through 5 would be I5. However, in this case, I3 and I5 are what? Yeah, the current going through each one of them is the same, right? So all we have to do is solve for IT, which is the total current in the circuit. All right, so I'll give you a minute to do that. All right, let's do it together then. All right, so how do we go about solving this problem? we know our Ohm's law, right? V equals IR, which means that we can transform it to current equals V over R because of math, right? We know what our voltage is. What's my voltage? 10. And we know what my total resistance is, which is what?
8.
So that leads me to 10 divided by 8, which is what?
1.25.
10 eighths? Yes, 1.25 amps. Very good. All right, so next we need to talk about the junction rule, right? And this brings us back to that universal truth, well, the universal truth of the universe, right? What goes in has to come out. Otherwise, what happens? If Andrew eats 10 pounds of food and he doesn't get rid of that 10 pounds of food somehow, what happens to Andrew? He may not get fat. Maybe he's getting beefcakey. I don't know, right? But he's going to get bigger, okay? And if we keep shoving stuff in Andrew and there's nowhere for it to go, what's eventually going to happen to Andrew? He's going to explode, right? So what goes in, right? It's all about mass balance, conservation of mass, conservation of energy, conservation of charge, conservation of everything. That's the universal truth, okay? So in this case, if we go into a junction, and what I mean by a junction is one wire going in and becoming two wires, right? So that would be the case of going from a power source and feeding a fan and a camera or something like that, right? The amount that goes in has to equal the amount that comes out, meaning I1 or I in has to equal I out 1 and I out 2, or I2 and I3, whatever you want to call it, right? So in this case, we have a split where I in has to equal I1 plus I2, and conversely, if I have a junction, which is a merge, I1 and I2 have to equal the total out. Okay, so this gives you one more formula that you can use, or one more set of formulas that you can use in your solutions of unknowns, right? Because if we have 4 unknowns, how many equations do we need to solve it? 4, right? We need one equation for each unknown, right? And then you guys can do your systems and go back through and solve it. Plug in and solve, right? But again, this is not a hard concept. You guys already have it, right? The total charge going in must equal the total charge going out. Otherwise, we don't know what to do, right? All right, so that leads us to parallel circuits. This is why a junction is important, because a parallel circuit is nothing but a whole bunch of junctions. So in this case, we can connect our light bulbs in such a way that an electron will only go through one of those bulbs, right? So in this case, an electron can go through this guy, he can go through this guy, he can go through this guy, and return all the way back to the battery without having to see the other ones. Yes? Why wouldn't it just go through the closest one? Because then you're trying to jam, effectively, like that would be like asking why doesn't everybody always drive the shortest way home, right? Because eventually somebody's going to figure out that it takes them less time to even go the extra mile around. You see what I'm saying? Yeah. I mean, that's a very basic explanation of it, but that's essentially it. Because if we shoved all the electrons through here, eventually you would get a backup and some were going to start flowing around, okay? The electrons will always want to take the path of least resistance, right, to the, and actually let's fundamentally explore what I just said, right? The path of least resistance is something you guys have always heard, right, but it actually means something, right? If I was shoving this entire voltage through this, the resistance would be higher, because then it would be effectively what? A series circuit, right? And what we're going to see here, so give me a second, we'll come back to that, okay? So in a parallel circuit, the voltage, so remember in a series circuit, the current was the same through each component, right? Because the same electron had to travel through. In this case, electrons can travel through different things. So what's going to happen is a balancing effect, like we were just talking about. And the voltage drop across each one of those is going to end up being the same. Assuming, well, it's the sum of, it'll be the same in the case where we have 3 similar lights, right? But the voltage drop across all of those components in a series circuit are going to be the same, okay? So when we look at a parallel circuit, the voltage and the current remain straightforward, but what can happen then to my resistances of the circuit itself? All right, so remember in our series circuit, I had 3 lights, let's say I had 3 lights that are each 10 ohms, that would then have a total resistance of what? 30 ohms, right? But in a parallel circuit, if I have 3 10s, do I still have 10? No, okay? Because what actually happens is this. Resistance in a parallel circuit because the current now is summation, we can substitute in for Ohm's law, and you do not have to learn how to derive this. It's one of the magic things about engineering, right? So this is what happens. If we substitute in Ohm's law, what we end up getting is voltage 1 over, because again, parallel, the current sum, it's a sum of the currents. So we put in basically Ohm's law here, Ohm's law here, Ohm's law here, out to infinity. And then you have to start doing factoring and all that good stuff. And what it comes down to is this. That 1 over, so the inverse of the resistance of a parallel circuit equals the sum of the resistances of the parallel circuit. So effectively, what does that mean? It means that the more resistors we add on a parallel circuit, the more loads we add on a parallel circuit, the resistance actually drops, right? So that's why it wants to spread out, is the more options it has, the more places it goes, the total resistance actually drops on that circuit, right? Now, there's another advantage. Come on, lots of clicks back. There we go, come on. Whoops. All right, there's another advantage to our parallel circuit. And we talked about it before. What happens if one of my bulbs breaks here? The other two keep going, right? Because it has multiple paths to go. When I go back through the derivation. All right, so on page 18 in your handbook now, we have another circuit to solve. And for this parallel circuit, now we have to start doing a little algebra. Okay? Let's find resistance 2, current 2, and current 1. So I want to work through this together, if that's all right, because this is our first time solving a big circuit, and we have to do a lot of plugging in. So first, what I want to do is I want to solve for the total resistance. So how are we going to do that? So I have two pieces of data that can help me with that. I have my voltage, and I know what the total current in the circuit is. So if I know what the total current in the circuit is, and I know what the voltage in the circuit is, what do I automatically know then with Ohm's law? The total resistance, which is what? It's V equals IR. So R equals V over I, right? Did I do that right? Okay. So in this case, we have then 8 over 6, which comes out to 4/3. So we're going to leave it in 4/3 instead of dividing it out. Why would we want to do that? Because when we go to our resistance equation, we start doing 1 over, right? So if we have a 4 over 3 and it becomes a 1 over, what does it then become? That's a lot easier to deal than 1 over 1.25, okay? Or actually 1.33, right? All right. So now we know what our total resistance is. Now remember, our total resistance is this whole group up here, right? Both of these guys together, right? So we have the total resistance, but we need to solve for this guy, and we need to solve for these guys. All right, so in order to find R2, we're going to put it into that nifty little equation we got, which is 1 over R total equals 1 over R1 plus 1 over R2. Now we know what R1 is, which is our 2 ohms. So it becomes 1 over 4/3 equals 1 over 2 plus 1 over x. And then we can just solve it. And what we end up with is that R2 equals 4 ohms. And why is that, right? 3 over 4 minus 2 over 4 equals 1 over 4. What's the inverse of 1 over 4? 4, right? You just flip it. Okay? So now we know that R2 equals 4 ohms. Okay, so now we have, this is a known, this one's been solved. Now what do we know about these two currents? Are they the same? No, they're different. Well, now what do we do? But we do know that what across those two is the same. In a parallel circuit, what's the same across each branch? The voltage. So now we just V over IR again. Okay, so now we've solved it. We know it's simply Ohm's law across R2, so we can solve for R2, which gives us 8 over 4, right? Because we just solved this. So we get 2 amps there. And now we have 2 ways to solve for I1. We could just add the currents together because we have 6 coming in, and we know that this is 2, so what does this have to be? By the rule of the universe won't explode. What's 6 minus 2? 4, right? Otherwise the universe blows up, right? So we can either call it 4 by just using our equation for current, or we can thus verify and check using Ohm's law across the known resistor, which of course is 8 divided by 2, which is what? 4. All right, so it checks. We did it 2 ways and it checks out. Okay, do I have any questions on that? I know that we kind of sped through the math here, but I'm also confident that if you guys are here, you guys can do that math, right? It's just doing algebra, right? Not fun, but it's doing it. Okay, so any other questions across that? So fundamentally, aside from getting the right answer, which I know of course is what we all want to do, what we're really interested to hear in the engineering class is the process by which we did it, right? So what we did is we started with we had to go solve for 3 unknowns in this case, and we only knew one of them, right? Because we were able to solve, we had the information to solve for one of those unknowns. Once we solved that one, we were able to use our knowledge of circuits using Ohm's law. We used Ohm's law like what, 3 or 4 times in solving this, right? Ohm's law across this, Ohm's law across this, solve for the whole thing, and then we used Ohm's law to get our current, okay? Or the junction rule to get our current, okay? So it's basically just an iterative process of using the information that you have to solve for the larger picture, breaking that larger picture down into smaller pictures and going through and solving the circuit, okay? You guys are going to be solving circuits for a whole semester, right? That's when you take this class, you'll be doing this a lot. And if you decide to be an electrical engineer and you get into AC power, good luck. But, all right, so now that we went through the actual math exercise of how to do that, I'm going to teach you guys some shortcuts. Okay? Parallel resistors are really cool in that if I have equivalent resistors, so if I have a 4 and a 4 in parallel, that is equivalent to a 2 ohm resistor. Why is that? Think about it. 1 over 2, or sorry, in this case 1 over 4 plus 1 over 4 equals what? 2 over 4, which becomes a 1 over 2, and then you flip that and it becomes a 2. Now, if I have 2 6s, that would be the same as a what? A 3, and 2 8s would be the same as a 4, right? You guys are getting what I'm saying, right? So on, so on. What if I have 2 1.5s? You'd still figure it out, right? It'd be 0.75. Okay, it works the same way. Okay? So when we have 2 that have the same resistance, and to be clear, this only works with ones the same resistance. If they are not the same resistance, this shortcut does not work. But why do we see this a lot in engineering? Right? You might not in circus class because your guy's trying to teach you something. Why do we see this a lot in engineering?
Because a lot of times you're using the same lights.
Bingo, and that's what I was going to point to. So these lights, if one of these lights burns out, because you guys have probably seen it around the school from place to place, I'm sure, right? I think that one's off intentionally, actually. But yes, you're correct, right? The point is, if one of these burns out, they'll keep going because these are hooked up in parallel. 1, so that if one burns out, they can keep going. But 2, what does it actually do to our power grid if we hook them up in parallel? We talked it's overall less resistance, which means it consumes less what? It consumes less overall energy. Very good that you guys didn't say electricity, you said energy. Very good. All right. So yes, consistently you will see things hooked up in this where they are equivalent because you're hooking up lights like this. You're hooking up, I don't know, I mean even these, the receptacles on the wall, right? The receptacles are the plugs, right? Receptacles on the wall are likely hooked up parallel, right? There's a ton of wire on the walls to make sure everything can work even when something else doesn't, okay? All right, and now the next shortcut, it's not limited just to 2 component parallel circuits. If I have 3 6s, that is equivalent to a 2. You can't divide it by 2. We instead divide it by how many? 3, because there's 3. And if I have 4 8s, that is the same as a 2 because we're now dividing our 4 8s by what? By 4, right? Boom, right? Super heavy stuff here. But hey, this will get you out of a lot of pinches. You can look at something and say, that's 4, that's 6, and it'll save you a lot of time. All right, so on 19, page 19 in your handbook, use the concept of equivalent resistance to determine the unknown resistances. So I have, what is that in the middle there? So I have a 3 and a 5 and 2 6s that are in parallel. What are those 2 6s equivalent to?
3.
A 3, okay. And now I have a 5, a 3, and a 3. What is that equivalent to? Why is that? That's not my shortcut, but why is it?
Series.
They're in series. So what do? Add them up. Very good. All right. So we just solved, right? We spent what, 2-3 minutes on the one before? This one we just solved instantaneously by saying, instead of having to go through and do the math, we said this is equal to 3 because it's one of our shortcuts. And now we know 3 plus 3 plus 5 equals, as he said, 11. Okay? All right, so let's just do a quick recap. A series circuit looks like this. The same electron has to go, and to be clear, this is not a complete circuit. This is just the resistors. Okay? Series circuit looks like this. Parallel circuit looks like this. In series, each resistor is on the same wire. In parallel, each resistor is on a different wire. The voltage is different for each resistor in series, but in a parallel, it's the same for each resistor, which causes, of course, us to have current that is the same in series, but different in parallel. And why that really matters is, to Tom's point, okay, the overall resistance in a series will increase as resistors are added, and in parallel, it will decrease as resistors are added. That's a pretty neat concept, actually, right? We can actually add more and more and more lights, and what happens? Our resistance goes down. But here's the trick question of the day from an engineering perspective. If my resistance goes down, what's going to happen to my current through those bulbs? It's going to go up. So will my battery burn out faster in a series circuit or a parallel circuit? Parallel circuit, right? Because remember, each one of those loads, when they're on, is still consuming power. So if I put a whole bunch of them on, I'm going to have really low resistance, which means my battery is going to drain like crazy, right? That means Bonneville Power is going to open up the floodgates. Salmon are going to be swimming for their lives, right, trying to get away because we're going to be turning on, trying to make more electricity. All right, so any questions there before we move on? Awesome. All right, so next that brings us to combination circuits. We've already looked at a couple of these. Combination circuits are really just, it's actually what the world is, right? We don't have, not all of our homes are hooked up in parallel. Actually, kind of they are, right? They're hooked up to the grid, kind of, right? They're independent. But what we've seen is two different ways of connecting series and parallel. The reality is most like actual circuits will exist with a combination of both of them, okay? So in this one below, which we've already seen some examples like this, what we have is we have a parallel set that's in series with two other resistors, right? So we have a parallel set that's in series, okay? So all we have to do is just do the rules that you guys have already done and go through and solve them in that fashion. So this brings us to the concept of equivalent resistance, which we kind of already talked about with our shortcuts. But equivalent resistance in a series, a 4 plus a 4 is the same as what? 8, because they sum. A 4 and a 4 here is the same as 2. We already talked about that with the shortcut. And an 8 in parallel plus a 4 series is the same as 8, right? So what you're going to want to do, like in an example like this, which will go on page 20, right, which we'll do in a second, what you're going to want to do fundamentally on this is ideally, when you're solving a circuit, you will reduce that circuit to being just one resistor. You will resist it to being your power source, just one resistor. And why do we do that? Because that lets you calculate your total current through the circuit, right? Because that's what we're interested in, because current is basically our electricity, okay? So if you could go to page 20, please. And what I'd like you to do is use your shortcuts. So you shouldn't need a calculator for this. Use your shortcuts to find the total resistance of the following what we call nested parallel circuit. All right, so Jeremy's going to walk us through. So what did you end up with your total answer?
My final answer was 1 ohm.
1 ohm, right? Is that what everybody else got? Right, I see nods. Yes, 1 ohm is the correct answer. So what did you do first?
I did the shortcut, so I knew each were 6 over there to the right. So, and there were 3 total, so I knew that was 2.
Okay.
And then I saw 4 and then 2, so that's 2 as well.
Okay.
But
So that left you then with what?
It left us with 2 and 2 in the shortcut.
Which becomes a 1 in the shortcut. Excellently done. All right, is that how everybody else did it? Nice and simple? Okay, you could math it out if you wanted to, but I like being fast. All right, so that's just to summarize, right? The generic plan of attack for solving a combination circuit is convert all the parallel components to their equivalent series, sum all the series, solve using Ohm's law, and then if needed, you can use the overall solution to back solve for the components, right? That's the plan of attack for every single circuit you're going to see, no matter how complicated. If possible, make all your parallels series, sum up your series, solve for your current, and then back solve. Clear as mud? Awesome. All right, so now let's get into the actual engineering portion of this, okay? So we understand how this works. We're all prepped. We all just passed Circuits 101, probably like a 121. Anyway, awesome. All right, so when we're actually doing the engineering designing, we need to actually think about what the function of what we're trying to do is for the proper designing, okay? And a lot of that comes in to resistance. So let's say, for example, I want to design a light, okay? And I want to have that, and for right now we're talking, actually let's not do lights because new light designs have changed. But let's say I want to make a heater. In order to have that heater make heat when I pass electricity through it, do I want it to have a high resistance or a low resistance? What do we think? What do you think? Why do I want a high resistance?
So it lets resisting it will create heat because it's resisting against the different molecules versus having that flow, it will have any resistance.
Yeah, that's you're absolutely correct, right? So when we put our current through a load, it is consuming power, right? That's what loads do, is they consume power. When energy, I mean, it's no different than physics, right? When we have friction in physics, what does our kinetic energy become? Becomes thermal, it becomes heat, right? It generates heat through friction. It's fundamentally the same thing here, right? The lost energy will become light in this case, but it also becomes heat, right? So you're transferring that energy from one form to another. Again, right? We come back to constant of the universe. Energy cannot be created or destroyed, just converted, right? So if I wanted to make a heater, I would, as he said, I want to go out and I want to select something that is high resistance because that's the function I want it for, right? So we don't always say, well, I want to save power, I want to save electricity, let's go find something that's low resistance, right? Let's now go use copper because sometimes you want to use, oh shoot, I'm forgetting right now, the it's 80-20, anyways, what you use on a stovetop. I probably have it in here. Sorry, I'm forgetting it right now. All right, so it's not lost on you that different loads behave differently, okay? Why does one light, right? You go into the store and there's like 90 million different types of light bulbs, right? There's a 40 watt, a 60 watt, whatever, right? Okay? Electricity is conducted through some materials better than others. This makes sense, right? Why would the electrician use big, heavy gloves, right? He uses big, heavy gloves that are an insulator so he doesn't get shocked, but yet we're using copper to actually transmit our wires, okay? So metals such as copper, like we already talked about with our hippie commune thing, right? They don't hold the electrons very tightly, so they conduct very well. These are called conductors, okay? Choo-choo, right? Other materials such as rubber and plastic, right, like the gloves that we're going to use, hold their electrons very tightly, right? They're in this big polymeric goo. Everything's stuck in there. The electrons don't want to move. So it takes a lot to bounce them out. You have to have a high voltage in order to shock the electrician, okay? So that brings us to the concept of resistivity. Right, so when we were talking earlier about we might want to go select a material with high resistance, and that's actually a misnomer, right? Resistivity is an inherent material property. It's called an intrinsic property. When I say an intrinsic property, do you know what I mean, Vikram? Okay, so an intrinsic property is independent of how much of that material I have, right? So if I have 1 pound of copper, that copper will have the same resistivity than if I had 200 pounds of copper, right? It's no different than the molecular weight of copper, right? The molecular weight of copper is still the same regardless of how much you have, and obviously the weight of copper will be different, right? But the molecular weight is an intrinsic property. It belongs to that material and that material alone. Does that make sense? Okay. So if we go, and let me shut off the lights just so you can read the table a little easier. All right. So resistivity is what we use to measure the ability to conduct electricity. And this is really just how difficult it is for the electrons to move through a particular sample. So aluminum, copper down here, right, they have times 10 to the negative 8. On the other hand, if we go to the other side of the spectrum, glasses and hard rubbers, and that's what I was trying to think of, nichrome. Nichrome 80-20 is what they use like on your stovetop. They pass on your electrical stove that gets glowing hot, so they use nichrome 80-20. Glasses are 10 to the 14th 10 to the 13th there for rubbers, right? So let's actually think about that, right? What's the difference there? Remember, a negative 8 and a positive 13 is actually a difference of how much? 21, right? 20, 21, in that range, okay? So that's actually a lot of zeros difference, if you guys think about that, right? That's to the 20th the difference. That's a lot of zeros. All right, lights or eyes. All right, so resistivity has the units ohm meters and is denoted by the Greek letter rho, which is unfortunate because what do we also use rho for? What's that? What's that? Say boats? Yeah. No, we use it for density. Oh, rho. Oh, I got it. I didn't kick it out. All right, sorry. The old guy in front's not getting it. All right, fair enough. All right. So because, like we talked about, it's an intrinsic property. It's completely independent of how much of that material we have. However, we know that we can build things that are different resistances total, right? Like you were talking about. And that goes back to my light bulb comment earlier, right? How can I go in and have a light bulb? So in light bulbs, incandescent light bulbs, we use tungsten as our filament, right? So we pass electricity through tungsten, it starts glowing, it gets really hot, starts glowing, just like it's the same principle as your stove, right? When you put the electrical through the stove, it starts glowing orange, right? Tungsten works the same way in a light bulb, except way hotter and way more, not really efficiently, but works way hotter. All right? So, sorry, I got off. All right, so yeah, so if we are, what we can do by designing our different, choosing different resistances, if we make something that's different sizing or a different shape, we can actually affect the overall resistance even though we're using the same material, right? And that fits back into our, it doesn't matter how much copper we have, but if we shape the copper in a different way, the resistivity will stay the same, but we can change the overall resistance by shaping it in a certain way. Okay? So the resistance of a material, the resistance of a particular sample can be determined including the following. R, which is our resistance, equals rho times length divided by the cross-sectional area. Okay, so that's a great formula. We can write it down, we can memorize it, whatever. But I want to functionally talk about this from a making sense standpoint. If I have to push through a long line of material, it's going to be harder for me to get my electrons through there. So meaning it will take me more energy to get my electrons through, or they will go through slower, right? The longer path I have to travel. Okay? On the other hand, if I have this huge area by which they can pass, they have more options to go, right? I don't have to go down that, right? If I have, like, let's say a single chain of atoms, I have to go through each atom, which means I have to wait for all my brothers and sisters to get out of the way before I can hop down the line, right? But if I have a big old pipe which I can go through, it's going to be easier to find a path. So the longer something gets, the harder it becomes to push electrons through there, which means our resistance does what? Goes up. And if I have a larger cross-sectional area, more options on which to go, that means my resistance is going to go down. Okay? And then the resistivity, of course, does that change? Not within the same material. If I want to get lower resistivity on the same size wire, what do I need to do? Change materials. Very good, sir. All right? So resistance will increase with length, and it will decrease with cross-sectional area. And that's why it's reflected in the equation in this way, right? Larger denominator means what? Smaller number. Larger numerator means what? Larger number, bigger number. Right? Very good, guys. All right. So that brings us to this. Right, my super fancy high-tech drawing, right? If this is our baseline copper wire, and I want to keep it the same size but get a higher resistance, what do I need to do? Go get nickel or something like that, right? Make it out of nickel or something like that to change the resistance. If I give it a larger area, I will have lowered the resistance using the same material, of course. And if I make it super long, twice the length but the same cross-sectional area, it now has a higher resistance. Right, so now we start getting into the engineering design side of you have to go and choose the right material, of course, right? And a lot of times that's the easy part. But let's say we want to make a 40-watt light bulb or a 60-watt light bulb. We now have to go in and decide, do we want to make our filament smaller? Do we want to make it larger? Do we want to make it longer? Right? And by longer in the light bulb, since they're all the same size, that just means we basically coil it more. Okay? Does that all make sense? Right? kind of unfortunate we had to have like 40-minute build up to the actual engineering part, which is actually conceptually simple, right? But that's the hard part, is actually going out and doing it, okay? All right, how are we doing on time? We're right on. All right, so that is the end of the lecture for tonight. So we will come back. We have circuits kits that we're going to play with, and we'll talk through that when you get back. But do I have any questions before the end? I know I started losing some of you there at the end with the resistivity. So any questions on that real quick? All right, I'm going to assume it's clear as mud then. We're good to go. All right, thank you guys. Thank you for watching Introduction to Basic Concepts in Engineering. Has this piqued your interest and you want to learn more? Much of the course content and the images in this course are from the text Introduction to Basic Concepts in Engineering for Adept High School Students by Andrew S. Heinz, PhD. While the textbook is not essential to successfully follow all class videos, it is an excellent resource designed specifically for introducing a student considering engineering to the field and for preparing them for the next steps. It contains many additional topics not presented due to time constraints, as well as additional practice problems and answers. The full text is also available on Amazon. Also, find us on Facebook at SHS Intro to Engineering.